Hello everyone, welcome to the course on Artificial Intelligence in Industrial and Management Engineering. We are talking about designing the process layouts. So let us continue from the last lecture. While designing these process layouts, what we have with us is the historical data. So let's say you are in the business of developing customized products and you have a workshop. So if you are tracking the interdepartment movements or the transfer of materials or workers from one department to another, then what you can do is you can utilize this kind of quantitative data and you can utilize it to develop a efficient space layout for your process layouts. So we start with historical or predicted material movement where between so this kind of information is provided by from to chart or load summary chart. Okay, now these charts shows the average number of unit loads that gets transported over time. So now what is this unit load? Unit load is a single unit a pallet or a crate. Okay, so as an example, a single auto in an automobile, a single car is 1 unit load. So now let us talk about these load summary charts, right? So let's say we have five different departments that are placed like department 1, department 2 and 3 department. Fourth is placed here and fifth here. Okay, so there are adjacent adjacent loads like 1 and 2, 1 and 4 and non-adjacent loads like 1 and 3 or 4 and 3. Okay, so we can develop a load summary chart for this simple diagram. So what we can write here is we can start with from to initializations. So this is from /2, then your departments, we have 5 departments, so 1 2 3 4 5. Okay, Now we don't have any movement from 1 to 1, right? So let's rule out these 2 and 2, 3 to 3, 4 to 4 and 5 to 5. Okay. Now from 1 to 2, from this to this inter movement department, the load is 100 units. Okay. From 1 to 3, the load is 50, and there are no loads from 1 to 4 and 1 to 5, right? For from second department, the load for third department is 200, and for fourth is 50. For third department to the first department, the load is 60. Then from third to fourth department, the load is 40, and this one is 50. Similarly, this is 100 from fourth to second department, and fifth to second is 50 only. Okay. So this is known as load summary chart, right? And these are your departments. So what information we are getting here is, let's say you have historical data and you have tracked what are the loads between two consecutive departments. So you can easily summarize your whole operations between your departments in this chart, right? Now we will utilize this chart to create a better allocation of these departmental resources in your space layout. So what we need to do is, we need to reallocate the department so that the load between adjacent departments is higher and non-adjacent department is lower. Why? So that the travel of materials, peoples or equipments between non-adjacent loads reduces, and it will overall reduce the cost of operations in your facility layout. Okay. Now let us create the final movements between these two departments. So we will first write the composite movements, and the loads. So composite movement is nothing but, let's say you have the data for the load between department 1 and department 2, and you also have the data for the load between department 2 and department 1. So the total sum of all both of these loads is your composite movement between 1 and 2, right? So the first load is 1 to 2, and since there is nothing between 2 and 1, because this is empty, so your total load is 100 units. Okay. Then let's say 2 and 3. So from 2 to 3 it is 50, and from 3 to 2 it is empty. So the total load is, from 2 to 3 it is 200, and from 3 to 2 is empty. So this is 200 units of load. Then 2 to 4 is 50, and 4 to 2 is 100. So this is 150, right? Then between 1 and 3, from 1 to third it is 50, and from third to 1 is 60. So this is 110. Similarly for 4 to 5, this is 60 units, because from 4 to 5 it is nothing, but from 5 to 4, 4 to 5. Okay, so this is also a load here. So from 3 to 5, this is 3 to 5 it is 50, and 5 to 3 is nothing, so the total is 50. From 2 to 5, this is 2 to 5 is nothing, but 5 to 2 is 50. So this is 50 units again. Then 3 to 4, 3 to 4 is 40 and 4 to 3 is nothing. So this is total of 40 units. And we can see here that 1 to 4 is 0. And finally 1 to 5 is also 0. So we can write here 1 to 4 and 1 to 5 is 0. Okay. So now what you can do is, based on these values, you will arrange your facility layout. This is your initial layout. Okay. And this is your revised layout that we will create based on the information about the composite movements. So you have no movements between 1 and 4 and 1 and 5. So here 1 and 4 and 1 and 5 are closer than third department, right? So what you can do is you can bring your third department closer to 1. Okay. Now let us try to revise our layout by first creating the same initial layout and start writing about what are the composite movements between these departments. Okay. So between 1 and 2, based on our composite movements, the load was 100. Then between 2 and 3 it was 200. Between 4 and 5 it was 60. And between 2 and 4 this was 150. And between 2 and 5 this was 50. So there were no load between 1 and 4 and 1 and 5. So this was 0 and 1 and 5 was also 0. Okay. Now there were some non-adjacent loads like 1 and 3. So 1 and 3 is 110. So we can utilize dashed arc between 1 and 3 because they are non-adjacent, right? And this is 110. Finally, another non-adjacent load was 3 and 4, right? So 3 and 4, this is around 40. So the total non-adjacent load is 1 2 3 and 3 to 4. Okay, so this was 110 and this was 40. So this 150 unit of load must be reduced so that we can gain more cost out of the better or revised layout. So how can we do that? We can put this 3 towards 1 and 4 because they both have the connection with this layout, right? Now let us try to move ahead and talk about different kinds of designs in product layout. So till now we were trying to design process layouts, right, where the product is customized. Now we are trying to design product layouts. These both are different layouts and thus their design is also different. So the machines or workers are arranged in a line in this layout. This we have already talked about. Now these they follow the order of operations that are required to assemble a product. So these order sequence are often based on bill of materials and assembly sequence. So we know that precedents are being followed for these product layouts. So precedence is that some operations come before or precedes other operations. But some operations can also be done concurrently. So that is why these precedence constraints are the key input for product layout designs. Now these layouts are useful for high volume productions. Okay. So to develop these kinds of designs, we need to divide each process into their subatomic processes, right? So jobs are broken into smallest indivisible portions. So generalizing these smallest portions is easier than to generalize a complete subpart, right? So this is the work element, and each work element gets performed by a single machine or a worker. But one worker or machine may perform several work elements. Now what is a workstation in this layout? Workstation. This is the area with at least one worker or machine. Now while designing these kind of product layouts, we need to identify how many workstations we require quantitatively, right? So we will do that. The layout decision is group work elements into workstations. and the goal of these design processes to provide smooth product flow through the complete assembly line. Through the complete assembly line. So how can we move our product smoothly in an assembly line? The easiest way is to, let's say you have multiple workstations identified, right? So the easiest way is to allocate each workstation is asking for the same amount of time to process the work element on that workstation, right? So when each workstation takes same amount of time, then the product will flow smoothly and there will be no bottlenecks, right? So there will be no waiting or idle time. And this the process of making each workstation time equal. This is called assembly line balancing. So this is one approach of designing your product layouts, right? Now let us talk more about what is a line balancing. So assembly line balancing operates under two major constraints. The first is precedence requirements, and the second is cycle time restrictions. So we already know about what is a precedence in while developing a product, but what is a cycle time is still not known to us. So let us first talk about the precedence requirements in line balancing. So this is the order of operation, right? And this we have not yet visualized any precedence constraint till now, but we can create different kind of diagrams to develop these, to showcase these precedence constraints. So they can be represented by a simple precedence diagram, and in these diagrams there are two things: node and directed arrows. So nodes are the actual work elements that we are talking about, and directed arrows are the constraints that needs to be satisfied, right? So these are the relationships between two work elements. So an example of a precedence could be that we cannot perform the operation of packaging a product before the constituent parts are attached. Okay, so this is a very simple example that if you have not assembled your products after performing all the jobs on that product, then you should not first complete the operations of packaging on that product, right. So this is how assembly line will work. It all those machines that are utilized for packaging operations should be placed at the end of the assembly line, while other operations that are required to be performed earlier should be placed earlier in the assembly line, right. So let's stop here in this lecture, and we will continue designing our assembly line in the next lecture with an example. Thank you.